So this is a short course. Can I see that? Yeah. On center manifold normal forms and bifurcation theory. And we're going to have, there's two different types of dynamical systems that we'll be considering. And those are continuous time. So an ODE, like x dot equals f of x. And discrete time. So x maps to f of x, or if you want x, if we have a discrete time with an index n, this is xn plus 1 equals f of x n. So these are usually called maps over here, and then these are ODEs. And you'll notice this is, I'm focusing on autonomous ODEs. So autonomous means that f is not a function of time. So x dot is dx by dt. And so we're talking about autonomous ODEs. If a system is a non-autonomous continuous time system, that would be x dot equals f of x and t. If this function f is periodic in time, then we can use a Poincare map. So if you remember from advanced dynamics, what a Poincare map was, for a time-dependent system, that would be looking at every, kind of look at the phase space after every period of the time. So then you get a discrete system. And what we'll talk about holds. But in general, if you don't have time periodicity, then the methods that I'm going to be describing here may not apply to the continuous time system. So if you have a non-autonomous continuous time system with aperiodic time dependence, that's sort of an active research question as to what are the methods that could be used for that. I may talk about that toward the end. So that would be, for example, the motion of a particle in a 3D turbulent fluid flow, or a 2D fluid flow, like the ocean surface. There is also something that can be said for these two types of dynamical systems. We're used to, in mechanics, dealing with the continuous time one, and then under special circumstances, we turn it into discrete time, like look at a flow map. So you take the ODE and say, okay, I have an initial condition, it flows for some time t, where does it map to? You get a discrete time system. So the discrete time systems are actually the more general one, because we could always turn a continuous time system into a discrete time map. So maps are, interestingly, the more general case. So for every continuous time, you can create a map. It's not the case that for every map, you can create a continuous time system that gave rise to it. So if we were to make a little Venn diagram, I guess we'd say types of dynamical systems are maps, and then there would be continuous time systems that came from maps, or that can produce maps. But maps are the more general one. There's also, there are dynamical systems with special structure, and A lot of times those come up in mechanics. I'll just put in quotes, special structure. What do we mean by special structure? Well, what we dealt with in most of advanced dynamics is Hamiltonian vector fields. So that gives rise to very special structure, and we have ideas of what the solutions will look like. There can be tori, quasi-periodic things. Also, if you have a Hamiltonian vector field, there's some behaviors that you cannot have, like asymptotically stable equilibrium points. So there's Hamiltonian vector fields. There's also things called gradient vector fields, and maybe I'll mention those at some point. That just means x dot equals f of x, where f of x is the gradient of a vector field. Sorry, the gradient of a scalar field. So a gradient vector field is where this f of x is the gradient of some scalar field. A special type of map that's related to Hamiltonian systems is symplectic map. The flow map for a Hamiltonian vector field is a symplectic map. You could also have reversible dynamical systems. So maybe some of you have taken thermodynamics and know about entropy. Because of entropy, like the physics of a macroscopic system is not reversible. So actual systems in the physical world are not reversible, but we sometimes approximate things as reversible, meaning for each final point, there's a unique starting point. So whether if your system has some special structure, it tells you a lot about the possible behaviors. So for example, you can't have attractors, things that are asymptotically attracting in Hamiltonian systems. And you can't have, this one might not be obvious, but you can't have periodic orbits in a gradient vector field. And if we do transformations of systems that have special structure, the transformations, let's say we do a coordinate transformation to kind of simplify the system. The coordinate transformation needs to preserve the special structure. So in advanced dynamics, we talked a lot about canonical transformations. Those are the transformations of the coordinates of a Hamiltonian system that preserves that it is a Hamiltonian system with some Hamiltonian function. All right, so this is this setting, what we'll be looking at. I'll often kind of first look at the continuous time, some results for a continuous time system, and then a discrete time system. Are there any questions about that before I go on to the next part? Okay. Well, kind of generally, what kind of phase space structures are there? There can be equilibria, and now I'm thinking in terms of continuous time. So if you have a point where the vector field vanishes, so there's no motion, if you start at that point, you will stay at that point. Those are equilibria. In the map context, we call those fixed points. So those are kind of the main skeletons. We sort of build up from small structures and look at how they relate to larger things. So equilibria would be the primary objects of interest, and then there are structures associated with the equilibria. So these are the invariant manifolds related to equilibria. So stable, unstable, and center manifolds. And you could also have other types of invariant manifolds. So this first type, we might call them, they're locally defined near an equilibrium point. You could globalize them, and like they might have structure that's over a large part of phase space, but they're initially defined in terms of the neighborhood of an equilibrium point. So they're local. You can have invariant manifolds that are global. So just larger, not necessarily associated to the neighborhood of an equilibrium point. So for example, the energy manifold in a Hamiltonian system or other systems related to mechanics that preserve energy, or a quasi-periodic torus. And you could have invariant manifolds within invariant manifolds. So let's suppose we have here's an invariant manifold, I'll call it lambda. And it's I don't know, maybe it's an energy manifold or just something else. It's some invariant 2D surface. Right? In mechanics, we could have things related to conservation of energy or conservation of some momentum. Mechanical systems are those with special structure. In general, let's just say we've got some invariant 2D surface. Then on this, we could have equilibrium points. So there's some kind of equilibrium point. An equilibrium point is a 0 dimensional because it's just a point, invariant manifold. We could also have periodic orbits. So here's some periodic orbit. Periodic orbit is it's a 1D invariant manifold. So you could have invariant manifolds within invariant manifolds. What do we mean by invariant? Well, if we, and I'll use phi of t. Let's say that phi of t is the flow map induced by our continuous time system, or by our ODE, x dot equals f of x. This means that this object, the flow map, maps from, so I'm going to say that our phase space is Rn, n-dimensional Euclidean space. It takes points in the phase space and maps them. So if you have some surface, some manifold, some collection of points, a set, it just sort of takes that and then maps it to where it is after some time t. So if you want to, these are initial conditions, and they are some subset of Rn, and then these are where they map to or flow to after some time t. So there's a picture that I've sometimes drawn, like, okay, here's M, our set of initial conditions, and it goes to something else. So if we have an invariant manifold, this thing that I've sketched out M is not invariant because all the initial conditions and everything moved away. But if we did happen to have a set where, let's call it lambda, and if we flowed, we would get the flow of lambda. So phi of t of lambda. If they happen to be the same thing, then this is an invariant manifold. That means it's invariant, doesn't change under the flow. So this is one such that the flow map of lambda equals lambda. This doesn't mean that each individual point maps to itself. If we did, then that would mean that you have just a collection of equilibrium points. But more generally, we're talking about a set of trajectories that when you map it forward under any time t, you still have the same set of trajectories. All right. So that's some terminology.
A quick question.
Yeah.
So I sometimes hear the term hyperbolic manifold used. What is a hyperbolic manifold?
We will get to what a hyperbolic manifold is.
Okay.
It's, yeah, we'll get to that. Yeah, I don't want to go too far ahead.
Okay.
Maybe I forgot, so I'm just covering myself. Yeah, it's as opposed to a non-hyperbolic manifold. We'll go to a classification system later where you can describe, it would start with equilibrium points in terms of are they hyperbolic or non-hyperbolic. And just very briefly, a hyperbolic equilibrium point is one where the linearized dynamics tells you everything you need to know about the phase space structure in the neighborhood of that equilibrium point. If it's non-hyperbolic, the linearized dynamics are not enough. You have to go to higher order terms to find out what's going on. But that's very brief. We'll say more about that. All right, so the next thing, because dynamics near trajectories is important to kind of building up this framework of, we'll look at equilibria, dynamics near equilibria, the invariant manifolds, and stable and unstable end up being kind of simple. It's the center manifolds that then take center stage and are important. So we're gonna, let me talk about linearized dynamics near a reference trajectory. And again, this is for a continuous time system. So if we have a trajectory x bar of t, so the setting is going to be x dot equals f of x, or x is Rn. Suppose we already know a trajectory and there's some trajectory we care about for some reason. We're going to call this the reference trajectory. We want to look at nearby trajectories. So nearby would be, here's some other trajectory. Actually, here's some initial point on it. Point on this. What happens to this other trajectory? So nearby trajectories, we could write them as just x of t without the bar. It equals x bar plus some displacement, which we'll call y. This is a displacement vector, and it's small. It needs to be small so that we're looking at nearby trajectories. We're looking at in the neighborhood of our reference trajectory. So here is, should be blue. the displacement vector. So x of t is x bar of t plus y of t. Then if we were to look at different moments in time, we'd have different y bar of t, y of t. So we want to know what happens to the displacement vector. And then knowing what happens to that displacement vector will tell us things about the reference trajectory. So we could ask questions like, is the reference trajectory stable or unstable? Or more generally, right, the linearized dynamics near it. So we want to get an idea of what is the phase space structure around this reference trajectory. Later on, we'll specialize to reference trajectories, which are just equilibrium points, because those are the simplest to analyze. But right now, it's a general reference trajectory. So then to get the dynamics around it, x dot equals f of x. That's just our dynamics. But then we'll substitute in how we're writing x in terms of, right, this is f of x bar plus y. And then we'll do a Taylor series expansion. So this becomes f of x bar. I guess let's put in that this is f of x bar as a function of time, plus df x bar. This is the Jacobian of the vector field f evaluated along the reference trajectory times y, plus, and then higher order terms. So these are terms that are quadratic in y or higher. And since y is small, the leading order dynamics will be given by that. So what do we also know? X dot is x bar dot plus y dot. But the reference trajectory already obeys this equation. So that means this term and this term are equal. So we're left with the dynamics of the displacement vector, which is y dot is d f x bar t y to leading order. So that means ignoring these quadratic and higher terms. That's what we get. Y equals 0 corresponds to the reference trajectory. And notice that y equals 0 is an equilibrium point of this dynamical system. This is another dynamical system. It's linear. So y dot equals an n by n time-dependent matrix times y. Maybe let's call this equation star. We haven't numbered any equation yet. So y equals 0 corresponds to the reference trajectory and is an equilibrium point of the dynamical system of the displacement vector. So if we look at the dynamics around the origin for this system, y dot equals a t y, where a as a function of time is just the Jacobian of the reference trajectory, some n by n time-dependent matrix. So the stability, or more generally, the local phase space structure. Around y equals 0 gives us the stability and the local phase space structure around the reference trajectory. So the question of the stability and or local phase space structure for the reference trajectory x bar is given by, at least to leading order, by this linear time-dependent ODE. Okay. So you could apply this if you wanted to any trajectory that you care about. So for example, I've done some work for NASA, and so their trajectories are just trajectories through the 3 positions and 3 velocities. So 6-dimensional trajectory through phase space. And if you want to know if a trajectory is stable or not, even if it's not a closed orbit, any trajectory, then you could analyze it using this method. But we're going to look at equilibria. And in equilibria, those are the simplest to look at. That would mean that x bar, which is usually a function of time, is not a function of time. It's just x bar, constant. And so this is the easiest case to analyze. Easiest case of a reference trajectory. You might even put trajectory in quotes, because how is an equilibrium point in a trajectory? It's the easiest case of a reference trajectory to analyze because A, which is df, the Jacobian evaluated at x bar, it's not a function of time anymore. So this is a constant n by n matrix, which is a nice simplification. Okay. So I think what I'm writing next will be review for, we did this in one of the first half of advanced dynamics at some point, right? So if you want to understand what are the dynamics for y under y dot ay, you do an eigenvalue, an eigenvector analysis of the matrix A. Okay, so let's say we get the eigenvalues of A. We're going to group the eigenvalues of A. So we have eigenvalues of A, and we're in the continuous time setting. Here is the real, the imaginary, and I'll use the symbol, I guess, lambda. So we have, I don't know what you'll get. You'll get something. We will group the eigenvalues of A such that there's lambda 1 through lambda s, and then lambda s plus 1 to lambda s plus u, and then lambda s plus u plus 1 all the way up to lambda n, where n equals s plus u plus c. So these first s lambdas, these are the eigenvalues with negative real part. So in this case, it'd be this one, negative real part. And then the next grouping, so we have s of those eigenvalues. The next group, which there's U of them, we have U eigenvalues with positive real part. So over here, this would be like these, just color them in orange. And then the next grouping, there are C of them. So S, U, and C are all integers. C eigenvalues with 0 real part. You might even wonder, why are these even mentioned? It's because they do come up and are significant. So 0 real part would be these things that are along the imaginary axis. And the way that we interpret these is, so for these eigenvalues, we have eigenvectors E1. So I'll write here the eigenvals, and here the eigenvectors. So the corresponding eigenvectors, and these are generalized eigenvectors. I'll say a little bit later, if you haven't dealt with what to do with complex eigenvalues, you turn complex eigenvalues into real eigenvalues, basically, and those are called generalized eigenvalues. And I'll go through an example. So the corresponding eigenvectors for the S eigenvalues, E1 through ES, and then these are ES plus 1, ES plus U. So there's U of these, and then ES plus U plus 1 all the way to EN. Why are we naming them S, U, and C? Well, you could take the local phase space, right? Here's y equals 0. It's our equilibrium point. And the phase space is Rn. We're going to write Rn as a direct sum of 3 subspaces, which are all like Euclidean subspaces. So Rn is ES, EU, direct sum EC. It just means that any vector can be written in terms of there's a component that's in this ES subspace, a component in the EU subspace, component in the EC subspace. ES, so we use E superscript S. The S is for stable. So stable subspace. This is the span of E1 through ES. The unstable subspace, E superscript U, span of ES plus 1 all the way to ES plus U. So this is S dimensional. This is U dimensional. The last one, the mysterious center subspace, E superscript C. It's the span of those final C vectors. So ES plus U plus 1 all the way to EN. So there were C of these. So this is C dimensional. So if you want to visualize what these subspaces are, if they were like, if it was 1 dimensional, it's just going to be a line. If it's 2 dimensional, it's a plane. If it's 3D, it'll be 3D. They're not curved. They're Euclidean subspaces. The curved parts come in when we look at nonlinear terms. And so that's where curved things like the stable manifold will be locally approximated by something that's Euclidean and straight, the stable subspace. All right. So for this example that I have up here, just this eigenspectrum, we have S equals 1, U equals 3, and C equals 2 up here. S equals 1. I mean, that's just for this kind of lame example that I showed. All right.
Can I ask a quick question?
Yeah.
What is the index you have on the last eigenvalue? Does it say n equals s plus u plus c or n plus?
N equals.
Okay, I just want to make sure.
Yeah, n. So we're looking in Rn, and so the s plus u plus c has to add up to n. I look at that and I think this means dynamics sucks, but it doesn't. So if you think dynamics sucks, that's an easy way to remember that. Yeah, it's just that the indices, that those integers have to add up to the dimension of the phase space because of this direct sum relationship. All right, so that means here's y equals 0, and then here's any other vector y, and suppose we have suppose as an example, I'll say s equals u equals 1. So there's here's E1, that's the, actually I don't want to do it that way. What color did I use? Green. Okay. Here's E1, and then here is E2. So you could write y in terms of there's a component in the stable subspace and a component in the unstable subspace, and then there's nothing in the center subspace because there's no center subspace. So you would just take, you take this and project it, take y, project it here, and this would be ys. Take this and project it, and you get yu or something. All right. If you have special structure, then that'll imply things about eigenvalues, and I don't necessarily want to go too much into that. If you have a Hamiltonian system, there's some constraints on actually what the dimensions of S, U, and C are. So in a Hamiltonian system, C has to be even dimensional. So if it's not 0, then it has to be 2 or 4 or something. And S has to equal U for a Hamiltonian system. But we said some things about that in advanced dynamics. I kind of want to get to the center stuff. All right, where are we? Okay. You probably know, or maybe you don't. If we have, I'll leave some of that up if you want to see it. So we've got y dot equals a y. That's our system. We know its eigenvalues. So near the equilibrium point, which is y equals 0, it's very useful to get the matrix in the eigenbasis. And so how do we do that? Well, you come up with a transformation matrix P. So here's a transformation matrix. And P is going to be an n by n matrix where the columns are the eigenvectors. So E1, E2, all the way up to En. So that's how we'll group things. So this just means that I'm writing the columns are the eigenvectors. Okay, and if you do that, then And sorry that I used lambda before for a invariant manifold. Now it's going to be a matrix. Lambda is P inverse A P. This transforms our matrix A into the eigenbasis. So whatever our kind of originally given basis was, we now want to go into the eigenbasis. So this is it's called the Jordan canonical form. And I guess I need to say here the generalized eigenvectors. So that means if you did have complex ones, you have rearranged things appropriately. So now you have only real eigenvectors. So this Jordan canonical form, it's just the simplest representation of your matrix. So transforming from the original basis to the eigenbasis gives us, there's where we did have y was our original set of coordinates. We now write P inverse y. So that gives us these are our new coordinates, the old coordinates. So yeah, how does this work? So take R dot, and P is a constant matrix. So this equals P inverse y dot. And we've got AY equals what? So if R equals P inverse Y, then this equals A P R. And what do we get is that Y dot equals AY transforms into R dot equals P inverse A P R. Well, this is just our dynamics written in the eigenbasis. So that's lambda. So R dot lambda R. So lambda is in this Jordan canonical form. It's going to be a block diagonal form. And it's the simplest way to write the dynamics. So you always want to work in the eigenbasis. Because it's the simplest representation. The dynamics. All right. So because I keep talking about these generalized eigenvectors, let me discuss the issue of what to do when you have complex eigenvalues. So we'll look at the simplest case, which is two-dimensional dynamics, and we have a 2x2 matrix A that has complex eigenvalues. I don't know if all of you have seen the idea of generalized eigenvectors. So the case of complex eigenvalues will definitely come up. They're what gives rise to the center manifold. So we're going to consider 2D dynamics. So we've got y dot equals ay, where A is 2 by 2 matrix with complex eigenvalues. So, I mean, A, hopefully it goes without saying, A is a real matrix. So if A is a real matrix, then if it has one complex eigenvalue, the conjugate must also come along with it. So that means it has eigenvalues lambda. I'll say lambda is A plus I B. A and B are real. And it also has the eigenvalue A conjugate, or A bar, which is A minus I B, right? So here is the real and imaginary complex plane. So we've got lambda, and then we've got its reflection across the real axis. Okay, so if you have a system that's like this, or A and B are real, it's going to have corresponding eigenvalues. So I could give you a matrix that you type it into MATLAB, and MATLAB just spits out the complex eigenvalues. So it'll give you corresponding eigenvalues. So corresponding to lambda, you'll have V, which is equal to, it'll be something complex, but it's going to have a real part, U plus I W. So if you want, U is the real part of V, W is the imaginary part of V, and lambda conjugate will have a corresponding eigenvector, which is the complex conjugate of V. So V is going to be a two-dimensional vector, U is a two-dimensional vector, and W is a two-dimensional vector. V is going to look like U minus I W, V bar, I mean. Okay, so this is what you do. U and W are the generalized eigenvectors. Even though MATLAB is telling you, no, V, this complex vector is what you should use. No, don't. So what we do is we would let P, the transformation matrix, be U as a column and W as a column. And we're just talking something that's 2 by 2. So
aren't U and W scalars?
no.
Because they form part of the eigenvalues. Oh, wait. Oh, no, wait. Oh, I'm just looking at this and it says with eigenvalues, V equals
Yeah,
U.
this will be like V, it'll be 2 components since we got a 2-dimensional thing. So this
I think you have a typo there because you meant to write with eigenvectors.
Yeah, that's right. Thank you. The eigenvectors. So this is what you would get from MATLAB. So if we let P equal that, so U and W are the generalized eigenvectors that form the eigenbasis. They're actual directions, like here's U and W. So then when we write our, write the matrix in its simplest form, P inverse A P. So we're writing the matrix in the eigenbasis. What we will get, and you can even work it out, you'll get this 2 by 2 matrix, which is A, B, minus B, A. So where in the original dynamics, the original coordinates, we have y dot equals AY, we do the transformation, your P inverse, R equals P inverse Y, or if you want, Y equals P R. So this is P R dot, equals A, P, R. Multiply both sides by P inverse. P inverse A, P, that. So we recognize P inverse AP is just lambda R. So in the new set of coordinates, say R1 dot, R2 dot, this will be A, B, minus B, A, R1, R2. And so this is the simplest representation. And you'll notice, yeah, it has that nice form. There's the A's along the diagonal, and then B minus B. So this is this matrix representation. This is the Jordan canonical form for the case of complex conjugate eigenvalues. So let's look at an example. Got about 20 more minutes. And this is just going to be a numerical example. So suppose we have 2D dynamics, and we've got a matrix that looks like this. Okay. You could find the eigenvalues of that, right? We first calculate the equation, the polynomial for the lambdas. So this is the determinant of lambda times the way I write the identity is like a giant one. So that's a 2 by 2 identity minus A. You get lambda squared minus 2 lambda plus 2. So what are the roots of this polynomial, this characteristic polynomial? Well, you get lambda equals 1 plus I, and we get its conjugate, 1 minus I. So, okay, using the above procedure, here we've got A equals 1 and B equals 1. If we did the eigenvector calculation, so the eigenvector for lambda is V, which is going to be complex, -1 plus I and 1. So we will write this as that we separate out the real part, -1, 1, and the imaginary part, 1, 0. So this is our U, this is our W. So P, the P matrix, which is the transformation matrix, first we write U, 1 or -1, 1, and then W, 1, 0. That's it. You could use the formula for how to write the inverse of a 2 by 2 matrix, and you'll get that. So then lambda, if you did lambda, we already know what lambda is going to be, but if you did the matrix multiplication, P inverse A, P, what you would find is it's A, B, minus B, A, 1, 1, minus 1, 1. So that's what you would get. This is writing the dynamics in the eigenbases. Okay. So that's the end of that example. If this had been here we did a 2x2 system. If we did a 3x3 system or a 4x4 system, and it has complex conjugate eigenvalues, well, we can deal with that. The V matrix will be n-dimensional, U will be n-dimensional, and W will be n-dimensional. But then you still kind of put it, put the columns as they should go. And so we'll look at an example of that. I guess what I want to say before that is, if we want to, why do we want to look in the eigenbasis? It becomes easier to interpret things, especially when we write the general solution. So hopefully you have seen the general solution for y dot equals a y, where a is a constant matrix. The general solution, it's that y as a function of time is e to the at times the initial condition. So this is the initial condition in the original coordinates. Hopefully you've seen a matrix exponential. If you haven't, the matrix exponential is defined according to the Taylor series expansion for the exponential for the scalar, but now you just put in the matrix. So the matrix exponential so e to the at is the first term is the identity matrix plus a t plus 1 over 2 factorial a t squared and so on, a t third, and you will get something. You'll get some matrix from that. That's in the original coordinates. What if we do the eigenbasis? So in the eigenbasis, remember lambda is P inverse A P, which we can reverse this and say that A is P lambda P inverse. Then Y T equals, right, the general solution is e to the at, initial condition, why not? And we could write we'll write A using this formula. So we'll get P lambda P inverse T, why not? And now this is a property of the matrix exponential. If it's raised, if you have e raised to P, some matrix, P inverse, the P can get pulled out. The P and the P inverse get pulled out. And so we're left with that. So that's just a property of the matrix exponential that I'm not going to prove to you. What is this? This is R naught. This is writing the initial condition, but in the eigenbasis. And then you could see we could multiply both sides times P inverse, and we'll get, so P inverse YT equals e to the lambda T R naught. This is just RT. So RT equals e to the lambda T R naught. So as we expected, in the original coordinates, that's what the solution looks like. In the eigenbasis, this is what the solution looks like. But usually here, e to the lambda t, lambda might be diagonal. And if it's a diagonal matrix, then that simplifies how you do the matrix exponential. It'll just be a diagonal matrix with e to the lambda 1t, e to the lambda 2t, so on. So let's do an example of that. So here's another example. This is instead of a 2-dimensional, we'll look at a 3-dimensional system. So A is 3 by 3. And we'll just say that we already know what the eigenspectrum is. There's going to be two eigenvalues with negative real part, and they're real, and then one eigenvalue of positive real part. So the way that we would group these is like lambda 1, lambda 2, this is lambda 3. So the eigenvalues, lambda 1 and lambda 2, they're real, less than 0, and lambda 3 is real and greater than 0. So we have S equals 2, U equals 1. So the eigenvectors are E1, so the corresponding eigenvectors E1, E2, and there's a corresponding eigenvector E3. We would construct this P matrix. These are dots just to show, we're writing the column vectors, writing the E's as column vectors, and then lambda be P inverse A P, and in Jordan canonical form with all distinct real eigenvalues, what we get is this matrix will be diagonal. So this will be lambda 1, lambda 2, lambda 3, with all other entries 0. So that means the dynamics nicely decouples in the eigenbasis. Right? The dynamics along the R1 direction is totally uncoupled from along R2, uncoupled along R3. Right? Yeah, this corresponds to R1 dot equals lambda 1, R1, R2 dot. So our system, which may originally have looked like it was coupled, A could have been a 3 by 3 matrix where all the entries were non-zero, but now it's nicely decoupled. Okay. In the original coordinates, so y of t equals e to the at y naught. But now we know that this will be written as p e to the lambda t, p inverse y naught. And like I said, as a property of the matrix exponential, here the matrix exponential is going to look particularly nice. It'll be just e to the lambda 1 t, e to the lambda 2 t, e to the lambda 3 t, with all other entries 0. P inverse y naught. And that's, this is a nice convenient way to write things. I think it's easier to work in the eigenbasis because then you just have 3 uncoupled scalar ODEs. Now the problem when you have a complex conjugate pair of eigenvalues is you won't have individual scalar ODEs. There will always have to be at least some 2-dimensional subsystem that's coupled. So complex conjugate pairs imply that there's these there's a 2D subsystem, and you can't get away from that. Maybe it's worth even saying here. So we have in the eigenbasis, all directions are uncoupled. So we just have 3 individual scalar ODEs. All right, so what about a case where we don't have all real eigenvalues? So here's another example. So I'm done with that one. Let's look at another. Again, a three-dimensional system. But with eigenvalues, we'll say it's there's a complex conjugate pair, and the eigenvalue is I'll call it rho plus or minus I omega. So let me sketch the eigenspectrum, where rho is negative and omega is greater than 0. So we've got something like that. So this is rho plus I omega, and here's rho minus I omega. And we need 3 eigenvalues, so the last one has to be real. And so we'll say there's lambda, and just for kicks, say lambda is greater than 0. Okay, so here's lambda. So this will give rise, the complex conjugate pair gives rise to a complex eigenvector, which is E1 plus I E2. So we're already writing that, okay. E1 and E2, what we're going to use is our generalized eigenvectors. And corresponding to lambda is E3. All right. You construct the P matrix, E1 and E2 as, right, these will now be 3-dimensional vectors. Write them as columns, and then E3 be our last 3-dimensional vector, written as a column. I guess we could say what's ES? Well, we've got S equals 2 and U equals 1, just like last time. ES is going to be, so the stable subspace is the span of E1 and E2. It's 2-dimensional. And EU is the span of just E3. It's 1-dimensional. All right. Y as a function of time, it's going to be P, e to the lambda t, P inverse times the initial conditions, where now it might not be obvious. It's not going to look as pretty as this thing up here, where we just have stuff along the diagonal because of the complex conjugate pair. Complex conjugate pairs give rise to, so in this case, we'll have, there's a portion that corresponds to e to the, rho omega negative omega rho t. And what does that give? This actually gives, if you work it out, you could work it out from that definition in terms of doing the Taylor series expansion. And what you'll find is this is going to be a 2x2 matrix of e to the rho t cosine omega t, e to the rho t sine omega t minus e to the rho t sine omega t, e to the rho t cosine omega t. So the in the eigenbasis, we'll have this 2x2 block in the exponential. So P, and then e to the capital lambda t will give rise to a 2x2 block. And I'll just rewrite what I've got over there. E to the rho t sine omega t minus e to the rho t sine omega t, e to the rho t cosine omega t. And then the third entry, so here in this little empty spot, is e to the lambda t. And then this is P inverse lambda naught.
Professor?
Yeah.
So this seems to correspond to the fact that there's some kind of rotation in phase space happening, right?
Yeah.
So couldn't we somehow put this into like R and theta form?
At least for that two-dimensional subspace, yes.
Yeah. But then
That's
we
right.
couldn't fit that into this big matrix. I'm just thinking of decoupling.
Yeah, and that's what we'll do eventually. Like when we talk about the Hopf bifurcation, that's exactly what's done, is it's studied in terms of polar coordinates on that 2D subspace.
Okay, okay.
And so that reminds me, maybe I could sketch. Here's our origin, and I'll just sketch what the dynamics looks like here. Wow, it's kind of weird looking. All right, so here's the 2D space of subspace of ES, and then I'm not sure what color to do the other one, so I'll do it. And these directions don't have to be normal to each other or anything. So here is EU. It's just the one-dimensional unstable direction. So what we would have on the stable subspace, right? We said that lambda is less than 0. So because of that e to the lambda t term, things will be spiraling in. And then because of the sines and cosines, we've got rotation. So if we had some initial condition in the stable subspace, it's going to be spiraling in. So decaying. That's only if we started exactly in the stable subspace. If we're a little bit above, what's going to be happening? So let's say we're a little bit above. There'll be some trajectory, and it's kind of hard to draw, but this thing is spiraling and going away along the stable direction. And if we started slightly below, there'll be things that are kind of spiraling and escaping along that direction. So the dynamics in general are going to be dominated by things leaving along the unstable subspace. So if you start above the stable subspace, then you escape along that kind of positive EU axis. If you start below, then you escape along the negative. If you're exactly in the stable subspace, then you just spiral into the origin. But of course, things will slightly be off in general. So almost all of the trajectories sort of leave along the unstable subspace. So this is the local picture of the dynamics near the equilibrium point, which is the origin. This kind of tells us everything we need to know. All right, there's some spiraling thing going on. In general, everything's going to leave because we have an unstable direction. Anytime there is an unstable direction, it will tend to dominate as time goes forward. All right. I mean, the least interesting thing that we can conclude from this is the origin is unstable. And sometimes that's all people want to know, you know, is the origin stable or unstable? Well, we could have gotten that from the eigenvalue analysis. Going to the eigenvectors tells you more about the richness of possible behaviors. And just because an equilibrium point is unstable doesn't mean it's worthless. It has value. They get used all the time. As you walk around, you are an unstable double pendulum, and that actually makes you more efficient. All right, so we've reached the end. It's 11:15. So we're going to end there and continue on, I guess, getting to the stable, or the center manifold, and this idea of hyperbolic versus non-hyperbolic next time. So